Well, today I'd like to take a look at where some of the equations come from in this chapter. We're going to be looking at kinetic energy, potential energy, and also energy stored in a spring. So we need to start with the work energy principle. The work energy principle tells us that the change in the kinetic energy of an object is the same as the net work done on the object. Now, how do we apply that? So let's take a look here. If we do some work on an object, we know from previously that that's force times distance times the cosine of the angle between the two. But here I'm going to push in the same direction that we're moving an object. And so I'm going to apply a force. And according to Newton, a force is mass times acceleration. When we substitute that in, we have mad work being done. If we look at some kinematics, just as an example here, this is the third kinematic equation that we often use, but we're assuming that we're going to start from rest, so the v initial t isn't there. And if we substitute that in, we find out that, oh, that's an ugly equation. Oh my goodness. Let's reduce that a little bit. Let's substitute something else. We also know that acceleration is change in velocity divided by time. So if we square both of those and substitute them where we have the a squared, we find out that the work done is 1/2 times the mass of the object times its change in velocity. But remember, we started from rest, so the change in velocity is just the final velocity. And so we find out that the work done as I push on something, making it go faster and faster, equals 1/2 mv squared. And if I've done that amount of work making it move, that's how much kinetic energy it has at that point. Let's talk about potential energy. You saw in the videos from Khan Academy that potential energy means stored energy. And if we use a non-conservative force, if we use a conservative force to store things in a gravitational field, that's called gravitational potential energy. If we use a force to compress or stretch a spring, that's a conservative force. We're putting energy into the spring. So let's look at gravitational potential energy. Well, just in general, when we do work on something, and it's a conservative force, the work done equals the stored energy. Gravitational potential energy looks like this. Once again, we see that work is force times distance. But if I want to lift this object up to some height, the force needed to lift it equals the weight of the object. So force is weight, mass times gravity, and the distance I lifted it, we usually call that height. So the work done lifting that object is mgh. Therefore, the potential energy that it has up here is equal to mgh. Now, let's take a look at storing energy in springs. Well, let me move this to a new location here. There we go. Got to move me up. So, you remember Hooke's law, I hope. Boy, I should have drawn a force here. If I have a mass hanging from a spring and I pull down on that spring, I change the stretch of the spring. And if you remember Hooke's law, it's linear, so it makes a nice graph looking like this. Well, the question is, how much energy did I store in the spring as I pulled down on the end of it? So we can find out. This time, instead of looking at work as force times distance, because we have a varying force, the force is getting bigger and bigger, we're going to look at the area under the curve. You recognize, of course, this is a triangle that we have going on here. So the base is going to be x, the height is going to be the force, and so we have 1/2 base times height, 1/2 fx. Let's substitute some things. We remember from a previous chapter, way back, force acting on a spring is the spring constant times x. That's Hooke's law. We're going to substitute that right here for F, and we get this big, ugly equation, 1/2 kx squared. So that is the amount of work done. Remember that K is how stiff the spring is. That's the spring constant. And if I did that amount of work, stretching it, then that is the amount of energy that is stored in the spring. So we often talk about elastic energy being 1/2 kx squared. Now, I guess in the next lesson, we'll have to start looking at the law of conservation of energy to find out how we relate all of these things.